abacus interface, it allows you to carry out various types of analysis. Okay? This one will fall under the category of a standard analysis. We can also do it using abacus explicit. So basically there are two schemes. One is the abacus standard and other one is called as abacus explicit. The key difference is that one solves the system of equations based on explicit dynamic analysis, and the other one solves the equations implicitly. Okay? And that's actually the type of FEM that we are covering in this course. We are not really going to cover explicit dynamic based FE in this course. That's more useful for dynamic problems, for problems involving high rate of changes in the strains. Okay? Now, the first step is that you actually create a model. Okay? So, your model encompasses all the information, or it needs to provide all the information that is actually related with the physics of the problem. Okay? The first step in every model definition is basically the part definition. You can have one part, you can have more than one part, and then you can actually assemble them together. Your part can represent a simple component of your system, or it can represent a subcomponent within a simple component. Okay? So that definition depends on you, how you want to define it. So for example, if you were going to simulate this fan, you can refer to it as composed of different parts, or you can make it all as one part. That's your choice, and that depends on the level of analysis that you're going to perform. So right now, this bar for which we have done this analytical solution, okay, that will be one part. It's a simple problem, so we just need one part, so we'll model it as one part. So we go to part, we click on the part module. Now we can actually model this as a 2D planar problem, or we can model it in the 3D space. It does not really matter that much. Ultimately we will be using truss elements, which are actually planar elements, but as you have seen, we can put those planar elements in a 3D space, right? So we can do that. So I'm going to choose a 3D space, and the type will be a deformable part because you are allowing your part to deform, and I will choose a wire representation because ultimately it's only those two nodes in a plane, so it's a planar representation of the whole problem that we are doing. You could have modeled it using a solid element representation of the entire bar as well, and that will yield slightly different results because then that will take care of the Poisson effects and take care of all those. But because we want to compare it with our analytical solution, therefore we are trying to use the same sort of representation as we have chosen in our analytical and our hand FE calculations. Okay? So wire part and approximate size, this number can really be anything, but right now because we have a 10 meter long rod, so I'm kind of just doubling our space of my canvas. So the actual size of the part will be what you actually draw. Okay? So this is just the size of the canvas. The units needs to be consistent. As long as you are using a consistent set of units, it will accept whatever input you are going to give it. I'm going to take everything in meters, okay, and of course then the corresponding consistent set. So forces will be done in newtons and stresses will be in newtons per meter squared or pascals. Okay, na? So that will form our consistent set. So